All right. So the first thing I want to show you, you just need to memorize, okay? And I'll leave it all up here for a few minutes. So this is, I know how y'all think. You hear statistics, and this is what your brain thinks, right? You start seeing sigmas and deltas and squares and z's and t's, and so we're going to go through this slide really slow. You can just write it down in your handout. No, so we're not going to do this, okay? But we're going to go and cover through these areas, and I apologize to those of you that already know how to do this. This is going to seem like torture because I realize about half the room has no idea how to do this at all, and these are really gimme easy questions. If you don't believe me right now, but I promise you, you'll be able to figure out sensitivity, specificity when we're done with this. I can guarantee you'll be able to do it. Okay? All right. So first thing is, how many of you can draw a square? All right. So you can either do the one I gave you in the handout, or you can get another piece of paper, but we're going to draw a square. So I want you to draw a square. Okay? You can practice doing that because you're going to have your little piece of paper or your board at the testing center that you can draw your square on. So practice that. So draw a square. Remember, it's 4 sides. What age are you supposed to be able to do that by? 4. Is that right? Okay, good. All right. So draw your square. Now you need to draw a cross in the middle. Okay, can you draw a cross in the middle? And by what age do you do that? 4 as well, is that right? 3 to 4. Okay. So 3 to 4 is a cross. Okay. All right, so you got the cross in the middle of your square. Now, here's the first part where people mess up. The first thing, okay, so what you need to do is at the top, what you're going to write is the word disease. Okay? So you're going to write disease at the top, above the square. Just write disease. So up here, you're going to write disease. So just write disease up here. So disease is up here. Okay? And you're going to put a plus sign here, or disease present, and disease negative here. So present, disease negative. Okay? Or disease absent. So disease is present in this box is going to be this column. Disease absent is going to be this column. Okay? On the side, you need to write the word test. Okay? And that's where people get confused. If you do that backwards, if you put the disease on the wrong spot or the test on the wrong spot, you're going to mess up. So don't do that. So remember, the way I remember it is, in the alphabet, disease comes before test, right? So disease goes on top. Disease is on top, test is on the side. And then again, you're going to have test positive and test negative. Okay? So you should have something that looks like this. Okay, that's what your little square should look like. All right? Everybody good so far? Okay. Now, so let's look at these people right here, this little box right here. So this box here. All right. So if we look at these people have the disease, right? So they're in the disease column. Everyone in this column here, remember up and down is column. So everyone in this column is going to have the disease, okay? And if you look at this row here, row straight across, everyone in this row is going to have a positive test, right? So this box here, where it intersects, is telling me that these people have the disease and the test says they have the disease. Okay? So these are our true positives. Okay? So if you want to put a TP in there or write out true positive, you can put that right there in this little box. So this is your true positives. Okay? Let's look at this box down here. Okay? So this box. So do these people have the disease? No. And what does the test say? They don't have the disease either, right? So these are the true negatives. So they're people who don't have the disease, and the test says they don't have the disease. So these are true negatives. Okay? If we looked at this group here, okay, so this box here, do these people have the disease? No. But what does the test say? That they do. Okay? So this would be a false positive. Okay? These are the false positive people. So they do not have the disease. They don't have disease, but the test says they do. That's a false positive. Okay? And then this last little box here, do they have the disease? Yes, but what does the test say? They don't. Okay? So this is a false negative. Okay? Now, really, the big ones you need to worry about for all these testing things is this box here and this box here. Okay? They're going to generally ask you about, you're going to need to make sure you can figure out what's in this box here and this box here. Okay? The reason is that when we do any kind of math thing, like an equation, like we divide something, the only thing that's going to be on the top answer, so the only thing that's going to be in the numerator, is going to be either this box or this box. Okay? So your true positives or your true negatives, one of these two boxes, depending on what we're looking at, is going to be the numerator. Remember, numerator is the top. Okay? So it's the top number when you're dividing something. Now, our denominator, or the bottom number that we're dividing by, is going to be a total. It's either a total of a column or the total of a row. Okay? So all of our tests that we're going to do here, sensitivity, specificity, positive predictive value, negative predictive value, the thing that's going to be on top is either this number or this number. Okay? So the true positive or true negative. So true is always on top. Something that's true is always on top. Okay. So let's look. So the next thing is you need to know, okay, and this is where people get confused, what do we use for sensitivity and specificity versus what do we use for positive predictive value, negative predictive value? And all you need to remember is for sensitivity, we're going to use the first column. So sensitivity is the column. First column is sensitivity. Okay? The second column is going to be specificity. Okay? So the first column is sensitivity. The second column is going to be specificity. The first row, okay, we're going to use for positive predictive value. The first row, we're going to use positive predictive value. The bottom row is going to be for negative predictive value. Okay? All right, we'll go through this again here in a second. So, if we look at sensitivity, okay, what we're going to use is, are we going to use a column or a row? A column. Which column do we use? The first column. Okay, so what did I say? So we're going to use this first column here, right? So what do I say always goes on top? True positive. Okay, so whatever this number is here is on top. And we're just going to divide that number by the total of the first column. That's sensitivity. Okay? So the true positive, this number here in this box, divided by the total of these two numbers here. Okay? And that'll give you the sensitivity. Specificity, what are we going to do here? We use a column or a row? A column. Which column do we use? The second. What goes on top? True. So the true negative is this box here. So this is on top, and then we're going to divide this whole column here by the total of the column. So true negative on top divided by the total of the column. Okay? That's specificity. All right. Now let's look at positive predictive value. So positive predictive value, we're going to use a row or a column? A row. And we use the top row. All right, so what goes on top? The true positive. So the only thing that's true on this row, and we're going to divide it by the total of the row. That's a positive predictive value. So true positives, this box here, divided by the total for the row. And the negative predictive value is we're going to use the bottom row, right? And then what goes on the top? The true negative, this box here, divided by the total for that row. Okay. Sounds simple enough at this point, right? Okay. So that's just saying, here it is all in words again. I'm not going to go through it again, but you can read it. It's just saying exactly what I said. So I'll say it again, though. I really want to hammer this home. So sensitivity, you take the top left box divided by the whole column. Specificity, you're going to take the bottom right box divided by the whole column. Positive predictive value, you're going to use the top left box divided by the whole row. Negative predicted value, you're going to use that bottom right box divided by the whole row. Okay? That's all we're saying. All right. Sometimes they ask you about this, and you just need to be aware of this simple little thing here. And it's about prevalence. If there's a very common disease, okay. So let's say let's talk about a very uncommon disease first. That's easier. So let's say Shushugamushi fever, okay. Shushugamushi fever. If I did a test on people in this room, and it's tested for Shushugamushi fever, and the test came back as a positive test, what do you think it's likely to be? A false positive or a true positive? False. Okay. And so so the positive predictive value of that test in a very low prevalent disease is going to be very low. Okay. So if you've got a low prevalent disease, your positive predictive value is not going to be very good. Now, if I had a test, let's say there's a test that says you're a pediatrician. Okay. And I tested people in this room, and it came back positive. Okay. That's going to give you a very high likelihood that that test is a true positive, right? So the positive predictive value of a test in a population where the disease is really common is going to be good. All right. If I did a test, though, let's give you a medical example. So let's talk about like lupus. So let's say I do a test of lupus in a 2-year-old child. Okay. So somehow the mother thinks the kid's got lupus at 2. All right, and then we'll make it a white child. We'll come up with a white male child at 2. Okay. All right. So you do an ANA on that kid. So if it comes back positive, what do you think the positive predictive value is going to be? Very low, right? You're going to have a hard time believing that that's a true positive test. So, but if it comes back negative, you're going to have a very high certainty that the kid does not have lupus, right? Because you came into the thing thinking, well, the prevalence of the disease is really, really low in him. I expect the test to be negative, and sure enough, it's negative. So the negative predictive value is really, really good. Does that make sense? Okay, it only works for those two. Sensitivity and specificity, it's not like that. They work without any idea of the prevalence, okay? It works, it doesn't matter about the prevalence for sensitivity, specificity. Okay, all right. So here's what happens on the test, right? So you're rocking along, you just answer that cardiology question that you knew, and then this thing pops up. And you see in a study of 2,271 patients with a history of colon cancer, you're like, well, that's an adult disease. But anyway, I'm going to show you can do this on an adult disease you know absolutely nothing about, okay? So this is how easy it's going to be. So you're reading along, 2271, fecal occult blood testing is done to screen for colon cancer. 146 patients have a positive fecal occult blood test. 2,125 have negative fecal occult. Colonoscopy is done on all the patients, finding 46 cancers. 12 patients with a positive fecal occult blood test have colon cancer, and 34 with negative tests. And your eyes just start glazing over, right? I mean, you're just like, there's numbers everywhere. And then you see they want sensitivity, and you just go, forget it. All right, so we're going to walk through this one. So I want you to get your piece of paper and draw a square. Draw your square. Put the cross in the middle. Okay, is everybody good with that? All right, what goes on top? Disease. So we're going to put cancer and no cancer, okay? So put cancer above the first column and put no cancer above the second column. And then what's going to be on the side? Test. So you're going to put test positive for the first row and test negative for the second row. Okay, we good? Okay. Now, there's all these numbers, right? And you start freaking out. Let's find a number that doesn't scare us first. So what I always do is I go find the smallest number on here. Okay, so look through the numbers. What's the smallest number here? 12. Okay, are you afraid of 12? Honey Badger's not afraid of 12. He don't care. Okay, so 12 patients with a positive fecal occult blood test have colon cancer. Okay, so let me think about this again. 12 patients with a positive fecal occult blood test, so the test is positive. So what row do you think I'll be on? Somewhere on the top row. And then they have colon cancer, so what column am I going to be in? The first. So where does the top row and the first column intersect? At the left upper corner box, right? So 12, dun, 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 goes in that box. All right? So the left upper box is going to be 12. So 12 people with colon cancer have a positive fecal occult blood test. Okay, is that good? Everybody good with that? Okay. I heard a no. Did I hear a no? It's okay. All right, so 12. I did not hear a no. No, or yes, I did hear a no. Okay. All right. So what's the next smallest number? 34. All right, let's look at 34. So 34 is still not bad. Some of you aren't there yet, and you'll see that 34 could be, as you gradually get older, maybe bad. But 34 people with negative test have colon cancer. Okay, so 34. So a negative test, what row is that going to be on? The bottom row, right? So negative tests are on the bottom row, and it's saying they have cancer. So what column is that? The first. So where does that number go? Okay, that bottom left box, right? So 34 is going to go there. Now, look what the question's asking us about. Sensitivity. For sensitivity, what do we use? You can use a column or a row for sensitivity. A column. Which column do you use? First, we could stop. You can stop. You don't need to do anything else, any other numbers. Okay, so how are we going to calculate this? You're going to do what? You're going to take which number goes on top, 12, and divide it by the total of that column. Now you have to add, and there is a calculator, so you can help. But so 12 divided by 46, right? You don't figure it out right now because we're going to. So you could actually stop right here. You could just you've already gotten to the point where you don't need to worry about any of the other numbers because that's all they're asking you for is sensitivity. Okay, but let's move on and see if we can figure out the rest of this. Okay, what's the next smallest number? 46. Okay, so it says colonoscopy is done on all the patients finding 46 cancers. Okay, what do? They told you the total of the first column, right? So hopefully 12 plus 34 adds to 46, which it does. Which, okay, you stupid people, I knew that already. You gave me something I already know. All right, so there you know you're doing things right because it should add up, right? The total first column is 46. All right, what's the next smallest number? 146, okay? So then it says 146 patients have a positive fecal occult blood test. Okay, what are they telling me? They're telling me the total of what? A row, right? The total of the top row. So out on the very end of that row, top row, you write 146 out to the side. Okay? So we know the first box is what? 12. And we know we need to get to 146. So how do we do that? Subtract. So do 146 minus 12, and that number is going to go where? In that top right box, right? Okay. And you get 134, right? Okay. Now, what's the next smallest number? Oh, it's getting big. Okay, so 2125, but it says 2,125 patients have negative fecal occult blood test. So what are they telling us here? The total of the bottom row, right? So can we figure out what the bottom right number is now? So we do 2125, you minus your 34, and you get 2,091. Okay, and that goes in that bottom box. So what you have is this box here we have 12, right? This box you have 134. This box you have 34. In this box you have 2,091. Okay? All right. So if we were going to figure out specificity, what numbers would you use? Okay, so you're going to use the right column. What number goes on top? 2,091 divided by the total of your column. Okay? And the total of that column is 2,091 plus 134, okay, which I don't have written, and I can't do it in my head anymore. So 2,225. Is that right? 2,225. Okay, so 2,091 divided by 2,225. Okay, that's your specificity. Now, let's say I want to know what the positive predictive value is. What do I need to do? Do I use a row or a column for positive predictive value? A row. Which row? First row. So what number goes on top? 12. 12 goes on top, and then what am I going to divide by? The total of the row, which is 146. So 12 divided by 146, okay, and that's going to be the positive predictive value. How do I figure out negative predictive value? Bottom row, I take which number? The true negative here, so 2091, and divide it by the total of the whole row. So 2091 divided by 2125, okay, and that'll give me the negative predictive value. Okay, are we good? Okay, so it's not that hard. Start with the tiniest number, and usually they're going to give you the tiny numbers are the ones you're going to be working with on the test. Okay, because they know, even though you may have a calculator or you may not, and they want you to try to get through the question, quickly. The biggest mistake people make is they put disease in the wrong spot. So disease is always on top, test is always on the side. Because if you reversed it, your answers are all going to be backwards. All right. So did y'all divide yet? 12 divided by 46. So go ahead and do that if you haven't done that. You can use your phone if you want to. And then we'll see if y'all can get this one right. And everybody look up here when you're done, and that way I'll know when people are stopped calculating. Except some people are sleeping, so it's hard to tell. Okay, so people good? All right, what do y'all think the answer is? Oh, it may not let me do it. Oh, it will. Okay. Yay. So 98% got it right. Okay? Now, the problem with, as you know, with these questions is each of these answers here is an answer to all the other questions, right? So so the specificity, if you calculate it, is going to turn out to be 94%. And the positive predictive value is 8.2%. And the negative predictive value is 98.4%. And that's what they do, because they know you don't know, you just know you divide something, okay? And so you think you're good. It's like, my answer's on here. I must be right. Yeah. All right. So the 2% that got this, you did a row instead of a column, okay? Remember, sensitivity is you use a column, okay, not the row. All right. So there's all the answers for you. Okay, so everybody good? At the end of your handout, I've got another exercise you can do at home on your own tonight. All right, and I promise you'll get it right. Okay, so go for it. All right, let's talk very briefly about p-value. A p-value we use is what you want to look for in a study to see is it statistically significant or not. So p-value is less than 0.05 is usually what you look for. So if it's bigger than a 0.05, then you're going to say it's not statistically significant. Okay? The lower, the better. All right. So, and then now we need to talk about these magic numbers, because they may give you some study, and you've got to interpret, was this thing that you did, was it useful or not from a statistical standpoint? And so generally what we're going to look for is magic numbers, either is the number 0 or the number 1. And we're going to have to remember a number line. You remember that from like 2nd or 3rd grade? Okay, when Louisiana it was like 12th grade, we finally got the number line. Okay? But you got to remember from negative to positive. Remember how the number line works, okay? So if you need to draw it on your paper, just remember -1, 0, and then +1. So usually for treatments and test results and survival, or they're talking about something like that, you're going to look for the number 0. If they say odds ratio or relative risk, okay, or they say OR or RR as abbreviations for odds ratio or relative risk, then you're going to look for the number 1. Otherwise, you're always looking for the number 0, okay? And the 1 here, the relative risk is compared to a human being, one person, okay? The average person is the 1. That's why we're doing it that way. The odds ratio or relative risk of you having this compared to the normal person, okay, the normal person's 1, and you have to decide, is it less than 1 or greater than 1? So if it crosses over that normal person, that means it's not statistically significant. I'll show you what that means. All right. So again, if it's odds ratio RR, it's 1. Otherwise, look for 0. Okay, so here's a classic question. A meta-analysis is done to see if blood glucose monitoring leads to lower hemoglobin A1C. Several studies are chosen for the meta-analysis. So here they give you this, okay? And I know your eyes glaze over again. You're like, oh my God, there's squares and there's a diamond thing and there's blue lines and black lines and there's a dotted line and I don't know what that is. And okay, so what you want to do when they give you something like this and they're trying to get you if it's statistically significant, look for the solid line, the solid up and down line. Okay, so not this one here though. Okay, not that one, but look for this one. Okay. So the solid up and down line. And generally, that's going to go to 0. Or it could be 1 if they're talking relative risk or odds ratio. But here they're talking about some treatment thing. Doesn't make a difference. And you want to look at 0. And then all you have to do, it's very simple. You follow along. You start out here on this study. You follow along. And does it cross over that solid line? If it crosses over the solid line, it's not significant. Okay? It's not significant. Now that little dotted line here, all it is there is to confuse you. You don't care about the dotted line. Okay? The dotted line is telling you the mean of this little diamond thing, which this little diamond thing is our meta-analysis. To combine all these 4 studies, we combined into one, and this is what you came up with. And so if you looked at it, you say, wow, you know, it's below, you know, it looks like it's pretty good. It's below 0. You know, it looks like there's improvement. But if you look at it, does the green bar cross over the solid line? It does. So that means it's not statistically significant. It seems to improve outcome, but it's not statistically significant. Okay? And if you look at all, and these big squares, all this is giving you the main confidence intervals for them. But you always want to look at the little tiny lines. These are the main ones we care about. There's a little tiny line crossover. So in all these studies, as you can see, it's not statistically significant. If you do meta-analysis, it's not statistically significant. Okay? So the question they would ask is, does glucose monitoring, you know, is it statistically significant? And the answer is no. And so you look for that answer, and it's answer D here. That's the only one that says it's not statistically significant. Okay? So D is the right answer here. All right. Okay. Now, sometimes what they'll do is give you the numbers and not give you a picture. And so here's some meta-analysis looking at whether breastfeeding protects women from developing breast cancer. 6 studies are deemed high quality. The odds ratio. So odds ratio, you see that? What do you want to look for? 1. Okay, and so what you want to see is, does the confidence interval cross over 1 on the number line? So if we start here, this 0.6, and you're like, wow, that's really a 60% reduction. That's really good. But if you look at the number line, it goes from 0.35 to 1.05. Does that cross over the number 1? Yes. So that means this is not statistically significant. Okay, it looks good, but statistically it's not good. Okay, it's not statistically significant. It doesn't make any difference because the average person is in the middle here still. Okay, so it's no better than the average person of 1. How about 0.6 to 1.1? Does that cross over 1? Yes, so it's not statistically significant. 0.7 to 1.22? Okay, crosses over, not. So all the other studies here are not statistically significant, right? Every one of them crosses over the number 1. Okay, so the answer here is A. There's no statistically significant evidence of protection from breastfeeding. Okay, do you see that? Okay, so here's another one. All right, so here's looking at catheters and saying, well, if we coat them in silver oxide, or we coat them in silver alloy. So these studies are looking at using silver oxide to see if it improves urinary tract infection rates. These studies are looking at using silver alloy catheters to see if they improve urinary tract infection rates. Okay? And then overall estimate, that's just doing like a meta-analysis. Okay? So here's an overall estimate for our silver oxide guys. Here's an overall estimate for the silver alloy catheters. Okay? Let's look at each study individually first, though. So where do we need to go? Well, how do we tell if it's going to be statistically significant or not? Okay, we look for the solid line. So the solid line, there's only one here, so that makes it easy. And it goes down to the number 1. Okay, so they're doing odds ratio, which they tell you down at the bottom. So you're going to be using 1. So this first study by Schaefer, okay, is this study statistically significant? Yes, okay, so you're like, wow, maybe this thing might work. But then they do another study. Is this statistically significant? No. How about this one? No. How about this one? All right. And then they do the meta-analysis, looking at all these, and pull it in, and is this statistically significant? No. So you see it barely crosses over, okay? Even if it crosses over a tiny little bit, it's not statistically significant. So silver oxide catheters do not reduce urinary infection, okay? Now let's look at the silver alloy guys down here. Is this one statistically significant? Yes. Is this one? Yes. This one? This one? Yeah, there's a tiny little space there. And then you do the meta-analysis, and it's statistically significant, okay? So what you could say is silver alloy catheters in these studies seem to reduce urinary tract infection, and it was statistically significant, okay? All right. Confidence intervals, you hear them talk about that. So confidence intervals, what we were just talking about when we showed you those numbers on that breastfeeding thing, right? So it was going from 0.5 to 1.2, all right? So as you're growing, when you see a range of numbers, that's a confidence interval that they're trying to give you. So in between parentheses is going to be your confidence interval, okay? So remember, it's 0 usually for a treatment, and it's 1 for relative risk or odds ratio. So as we said, this clinical breast self-exam and reduced death from breast cancer. The relative risk is 0.8, which sounds good, but the confidence interval goes from 0.6 to 1.2. That crosses over 1, so it's not statistically significant. Good? Okay. Number needed to treat. Okay. This is the number of people needed to treat to prevent one bad outcome. Okay. So you're going to see this a lot. You see this a lot in the literature, especially in evidence-based medicine, because it's very helpful to figure out, is it really worth doing something or not? Okay. So let's say I invent this drug that prevents, let me think of something, ADD in kids. Okay. Let's say I invent this drug, and I think it may prevent ADD in kids. Okay. So what I'm going to do is I'm going to run a study where I have a placebo group and I have a treatment group. Okay? So there's going to be kids who get my drug, and there's kids who are going to get a placebo that's not my drug. So if we look at the placebo group, how many of those kids are going to get ADD? So we have 50 kids enrolled. 20 of the kids end up having ADD down the road. So 20 out of 50, or 0.4, are going to get ADD. Okay? So that's the people who didn't get my drug. The people who get my drug, the kids who get my drug, we start with the same number 50 here. And in that group, down the road, 10 out of 50 end up getting ADD. So it's only 0.2. Okay. So then what they want to know is, what's the number needed to treat? And so what you do is you take you need to look at the absolute risk reduction, which is what you do is you do number 1 divided by the rate in your placebo group minus the rate in your treatment group. Okay? So what was our rate in our placebo group? 0.4. What's the rate in our treatment group? 0.2. So you do 0.4 minus 0.2. That's 0.2. And then you do 1 divided by that difference. So 1 divided by 0.2 is 5. Okay? So I have to treat 5 kids to prevent 1 case of ADD. All right? So that's good. You want that number to be small. If it said I had to treat 2,000 kids or 50,000 kids to prevent 1 case, then you're not going to ever market that drug, right? No one's ever going to look at it. So you want to look for a number needed to treat to be small. Okay? You want number needed to treat to be small. Okay? Is everybody clear on that? So you find out the rate in the placebo group, you find out the rate in the drug group, subtract that, and then you do 1 divided by that difference. And that's the number needed to treat. Okay? All right. Just real briefly on study designs. They may ask you, sometimes they ask about this. So a cross-sectional study, that's like our weakest study. That's like if I said, okay, we're going to do a study in this room, and I'm going to look for some factor and see how many people in this room have this factor, and then it's just kind of like no one does this anymore, okay, because it doesn't help you with anything. So a cross-sectional study, pretty much, you're not going to do anymore. The conclusions, no, you really can't get much out of this. You may tell you, well, here's some group, and here's the prevalence of that disease maybe in that group, but it doesn't necessarily correlate with any other specific groups. And you really can't, there's no way you can figure out cause and effect, okay? So case control study is kind of the easier study that's been done, or the least costly of some of the studies. And here what you want to do is, generally it's a retrospective. Generally, for the most part, they're retrospective, so you're going to go back in time. And so what we might do is we look at people who have disease and people who don't have the disease, and then go back in time and say if they're exposed to this risk factor. So an example would be, let's take current Alzheimer patients and non-Alzheimer patients and look back and see if they drank coffee as teenagers, okay? And if you see a higher rate of Alzheimer's in people who drank coffee as teenagers, then you say, okay, maybe there's an association here, okay? Maybe coffee drinking in teenage years is associated with Alzheimer's. Obviously, the problem is you didn't control for anything, right? You're just looking at current patients, and you're picking one thing and saying, well, did this one thing contribute or not? And that's the problem with some of these studies, and you'll see they'll get published in some of these bad journals or something, and then the media will get pick up on it and go, this hysteria starts. And there's really no cause and effect here. You really can't prove cause and effect. It's an association. And so you might do it as an initial thing to say, hey, is this something we're worried about? Then we want to do some other study to really see if this makes a difference. So case control is good if you're thinking about a possible association and you want to try to prove maybe that this is something you might want to investigate further. And it's also really cheap to do compared to the other studies. Okay? It doesn't involve, going in, having patients and following them and things like that. A cohort study is usually prospective. You can do these retrospective too. But here what you're going to do is divide subjects into groups based on whether or not they have the risk factor and follow them into the future. So we're going to take coffee drinkers and non-coffee drinkers in their teen years and follow them for 40 years and see who's more likely to develop Alzheimer's. Okay? Again, there's a lot of co-founders there or confounders there, but it's more likely to show a cause and effect. Okay? More likely to be able to show a cause and effect because you're actually looking at real people and really seeing whether or not this is going to be a problem or not. What you really want to look for in a test question, which they'll ask you about, what's the best trial you can do, and it's a randomized control trial. Okay? Randomized control trial is the best you can do, and this is a prospective trial, so you're going to be going forward. And what you want to do is, like we start today, we want to randomize people into receiving a treatment or not receiving the treatment, and then we want to blind the patient so they don't know if they're getting the treatment, and then you want to blind me as the researcher. I don't know who's getting the treatment, so that I'm not biased when I'm looking, hoping my drug's going to be good, and say, oh, wait, they're better. I think they're better today. So you don't know. You don't know which way. So the patient doesn't know what they're getting, and you as the researcher doesn't know what they're getting. So an example is, let's say we want to look at ACE inhibitors or placebo in our adolescent diabetic patients and see if those given the ACE have a less risk of developing renal insufficiency when they're adults. Okay, so this would be a prospective trial, and they get placebo or not, and then you would be blinded, and then you'd follow them and see, is their creatinine rising or not down the road. Okay, so best study. All right.